Hello YouTube, what's up guys? This is Mainak and today we will do the structural design of a building which a friend has given me, and I thought that I'd show you guys the updated process of completing in STAAD software, STAAD.Pro by Bentley. So I'm just choosing a pretty much small building so that I can show you the entire process and not make the video very long. And also I am planning to just give more complicated buildings as well from some of my projects. So I'll give a complicated structure also, but this is so that you can grasp the entire process, which is the updated process within a few moments. And also I keep updating my process, and also I take feedback from all of you guys that what is, if there is anything which I can update about my process, and also I tell you what are the things I want to update. Okay, so too much talking is done. So once we have a plan here like this, in we have here, and we can also obviously make a CAD file, but I have got a PDF file, so I don't want to make the CAD file right now. I'll make in I think another video. So I'm using Foxit, this PDF reader, so that is pretty good. You can type a lot. So I'm taking this as my 0 axis. I'll just do the coordinates here. So I'm taking this as 0. When you type the first letter, it takes some time to just get ready depending upon your system, so that's why it's taking some time. So I'm just taking the first letters, 0, comma 0. So this is the my first coordinate here. And if you know, here in STAAD, which I have already those who are experienced users already know, we have the axis like this. If you go to the top view in the STAAD model, you have the axis like this. And here this is the positive z axis, and in this, along this is the positive x-axis. So here the positive x and positive z, or z, whichever pronunciation you may take. And so this is, if this is 0 0, then suppose this particular coordinate will be here 3.288. This is the distance in this direction, and the z-axis also we're taking as 0, so it will be 0. Okay, so again the next coordinate here, this one will be, just take this, we use the calculator to just calculate the average approximate distance here. So 3.288 into 2, if we do 3.288 into 2, if we do, then we'll get the 6.576, which is this plus this basically. So 6.576, which is this value, and comma 0. So this is the coordinate here. So these are the column coordinates. Let's do the column coordinates first, and then I'll tell you other things. That basically we have to do all the coordinates where there are joints, or we can choose to draw only the columns. We want the column coordinate, and all the secondary views we can do in the software later. So that process I am preferring nowadays, doing the columns only and then the secondary views later. Okay, so let's go by that only. So here what we can do is I can actually copy this from here. Let's see if Control C and Control V works here. Yeah, this works, definitely works. So I'll move it over here. I might delete that later. Okay, 0 comma 0, only in place of the z coordinate we'll write 3.538. okay, so this will be the coordinate here, 3.538. this is the coordinate here. If I can, I'll delete this. Let's delete this, why not? Okay, so Control C, and I'll just Control V, paste it here. By the way, if you don't have this software, you can just do take a printout, or and then do it in the paper itself, or any other way which you can do. Take a sniping tool, you can just take the snipe and then do it there. So there are various processes. So only this this z coordinate we need to just check here, 3.538, and this one is this. And just copy this and paste it again, bring it here, so that is visible, and only the z coordinate changes, 3.538. so yeah, this done and dusted. And let's just copy this 3, I think doesn't copy together. 3 selected, Control plus C, Control plus V. Let me try. Okay, yeah, 3 are copied together. That's fine. And let me try that one more time. Control plus V. Yeah, that this also worked for this. Okay, so I just found this picture. Okay, so 3.538 and plus again approximately will be 2.075. By the way, I should take center to center, but I'm just taking approximately here, just for showing this. If you take actual center to center, I have to do a CAD file or do a lot of calculations, so that's why it won't make that much difference here. So 3.538 using the calculator, 3.538 plus what's the value, 2.075. 2.075 is the value, so the total value comes as 5.613. so we just want to replace this with 5.613 here, 5.613, and I can even copy this. I think, yeah, I will copy this, Ctrl plus C, and then I can paste it here. I also just right click and paste it here, and this one is sorry, this one, the z coordinate will be different obviously. So 5.613 plus these two values, 2.338. Okay, so let me just do this. 5.613 plus these two values, we have 1.075 plus, and this is 2.338. so 2.338 at a 9.026. so this will be 9.026. I can copy this, copy, and paste it here and paste it here. Okay, so that's it. I think this secondary beam we'll do later. I think we'll have one secondary beam here, and that is also good. This plan had a secondary beam because I want to show you how to release the moments here. I think we can avoid this this one also, this beam, not that much significant. Okay, if you want, then I'll also give this also. Okay, why not? So this is the plan here, and let's do a G or G+1. Let's do a G, ground floor only building, and this particular thing, this will do as the headroom. Okay, ground floor, and then we have the staircase for future expansion or going to the terrace. Okay, so let's open here. The coordinates are done, and let's open this folder and we'll just create an Excel file. I don't have Excel. I use WPS. It's WPS. So in Excel you can just use this. First just type, I'll zoom in a little bit using just so serial number and X and then Y and then Z here, and this serial number is 1 here, and first of all let's do the coordinates here one by one. So let's do the first coordinate, 0, 0, 0. Why we are taking the plinth height as 0? So anything below, that is the foundation level, which will go, this will be negative, and above height will be positive. So everything Y will be 0 here for the plinth level, and yeah, so the next Z coordinate will enter here. This is also 0. Okay, so I think I'll pause the video and enter all the coordinates without recording. So I have updated the process here, and you can see these are the coordinates which are having. So first of all, these coordinates are done here for all the columns. All the points have the columns here. So we just open the STAAD.Pro software. Okay, so I am using the STAAD Connect edition, and some of you might also use the STAAD Select series also. So there is not much difference, basics are the same. So firstly we need to create a new building here, sorry, folder here. I'm just telling building, I'm just always thinking about buildings. So yeah, so yes, live session, this is I think project 10 of my session. Okay, and I'll just create a folder because STAAD creates many files. You don't want the folder to get clustered, so I'll just name this STAAD file, because you want to create a folder specifically for the STAAD file. Otherwise you won't, there will be many folders in your files in your folder. Sorry, I'm just Okay, so I'll just name this one, and then we'll just use metric as our units. So create. So now you have this node feature, and yes, okay, let's get that done here. And this one, we'll just copy this 12 nodes which we have, and then we'll just select this and Ctrl plus V, paste it. And here you have the nodes here, view, and we'll go to the top view here, and we'll use the geometry option. Go to the geometry tab, and we'll use the add beam option, and we'll add the beams. So it's pretty relaxing. You can use this for ASMR if you're watching without practicing. By the way, I recommend that for this video and most of my videos, you just open your STAAD, your AutoCAD, and whatever the nodes which I provide, which are downloadable for free, and then practice along with me. That's this way you can learn. Or you just if you are already experienced, you just want to revise the concepts, you can also see this, I guess, and revise the concept, which I also do that. Watch the content creators at 2x. So just can see now these are the nodes, and I want to copy the nodes to the foundation level. Let's assume that we're having a foundation depth of 1.5 meter and a plinth height of 0.45. So let's go 1.95 below to reach the foundation depth. So we'll go to select cursor and node cursor, and select like this. We can also use Ctrl plus A, and we'll go to geometry, and we'll use the option of Y direction, that is the vertical direction, and the spacing will be minus 1.95, which is the spacing which you want to give here, and click here, and then click on link steps, and then click on OK. So you can see the structure is ready here. And I want some secondary beams also to be a part of this plinth member. By the way, in plinth beams mostly you can avoid the secondary beams, but in large section it's recommended that you do. So just for showing the process, I'll just show you here like this, and click on new view and click on OK, so that I only work on this particular structure. We'll go to the top view here, and in the top view I'll create the secondary beam. So secondary beam for this toilet I will create from here to here, because this cannot go in mid-air, so it has to be from here to here. So it is 1.075 from this particular column here. So from this particular beam here, this is approximately 1.075. It's not accurate, not the center to center distance. Select this, Ctrl plus C and Ctrl plus V. By the way, in projects you should be most as accurate as possible. Okay, so you can use AutoCAD for that. So yeah, so 1.075 is along the Z axis. You can see the X coordinate axis, Z here, X here. So this should I use the magnifier? Okay, so no, I just forgot the value. 1.075 along the positive Z axis. Click on OK. Done. So now we can see the beam is automatically divided here. We don't need to do anything, but this particular beam is a secondary beam. So we have to release the moment, and in STAAD we release the moment only in the Z direction. Can just Google that and see why. Otherwise I might make a video to explain it. Okay, so you have to release the moments so that no moments are transferred here, because these are pin connections, not fixed connections. Okay, so enough. Let's release the moments here. I think we'll release the moments later, because I want to go step by step. Like for the example, right now we're in geometry, then we'll go to properties, then material specifications, supports, then loading, then analysis, then design. If we go serial by, then we are less likely to make a mistake. That's why. So that's why I am just following this. Otherwise you could do it now. Okay, so we'll release the moment of this later. Okay, so now we can just go to this particular view and display whole structure. We can copy this beam to the next level. And in the roof, if we have this similar design, then we need this, otherwise we don't need this. Let's assume that we have a similar design for obviously if you're modeling a single floor, then we don't need this. Just remove this, and then I'll press Ctrl plus C. We want the link steps to work, so that's why I go to geometry, and then we use the option of translation repeat here. Let's assume that the floor to floor height is 3.2 meter, which is 10 feet 6 inches for those who are familiar with those units, and 3.2 meter and 3.2 meter, and just click on this link steps, because why you're clicking link steps now? Because all the members have the column connections, and if we if you are to also include the secondary beams, then we couldn't use this, we would use the additional step. Okay, so so that's why I'm using the link steps now. Click on OK. Now so this is done, and we want to also go here and select this view and right click new view and click on OK. So I just want to show you obviously this extension, this portion, and I'll go to geometry. Let me just change the view first. Select this and change the view to the isometric view and display whole structure, and go to geometry, and then translation repeat, and then in the y direction this will be, let's suppose the headroom height or the mounty, most people call it mounty, or headroom or staircase room, whatever you call it. So the mounty height, let it be 2.4 meters, and use the link step option here and click on OK. So yeah, this is done. You see nice little building here, geometry, and for now all the steps in the geometry are completed. I think I did a mistake here. I think we included this also in this selection by mistake. Okay, so we'll just yeah, we should have deleted that. So we'll delete. Okay, this is good, it's all planned. So how to get out of this mistake, I'll show you. So this is the beam is two parts because we have a secondary beam here, but here we don't have, you know, two parts here. We don't have a beam between, so this should be a single line. So how to do that, I'll just show you. For that I made this mistake intentionally. Just okay. Okay, so select this, and then we'll go to beam tools, and we'll use the option of merge beams. So this will get merged and this will get merged. So now we can see this is a single beam. So yeah, so that problem is fixed. Now geometry part is complete, and then we'll go to properties. Okay, so now in properties we define the properties of the columns of the beams here. So rectangle properties here, we'll go with 0.3 into 0.3 for the columns. Let's go 0.35. Let's go 0.35 into 0.35 for the columns here, and then for the beams we'll go for the plinth beam 0.35 in, sorry, not 0.35, 0.25 into 0.35 for the plinth beam, and for the roof beam we'll go a little bit more. Let's go 0.25 into so if we include the slab height, suppose if we want 3.35 as the hanging part and the slab height as the 0.125, then it is 0.475. okay, that seems a little bit more, so we'll go 0.35 plus point okay, let's go 0.4. okay, let's go 0.4. let's see, 0.4 for the beams, 0.25 into 0.4 at, okay, close it. Now as we have to assign this, so select this and go to select parallel to Y, since these are for the columns, assign, and yes, this is for the beam, plain beam. So sorry, I've used shortcut I was telling you, so I'll just do it again. So there is a shortcut. If you just click here, left click, and then press shift plus 1, then it goes to the front view. Okay, so this can be used to select the beams here, assign to selected beams, assign, and yes. Now for this, again click here, go to the, use the control plus 1, sorry, shift plus 1 hotkey, and then assign and shortcut key. Just those who play games know about hotkeys, right? That's similar to that. So in this is also a roof beam potentially, but I'll go with this one, right? The plain beam option should be sufficient, but if you want like put some overhead tank or something like this, then I think this design will get passed. Okay, so I'll use this anyway, assign. Okay, so yeah, all these members are assigned. Now you need to do some mandatory checks. They go to the node tools and remove orphan tools node. If there are any orphan nodes, then it will get check the duplicate nodes, no duplicate tool, nodes found, beam tools, zero length, no zero length found. So you can check this so that you know if you have any error, then you can find out. So, and also there's one missing property option. If you, and there is any object which you have not defined the properties to, you can do that. So that's a good habit to have actually. So yeah, so go to a view here and select this view. So here now this properties part is done. Now we can use a hotkey or shortcut key, shift plus, sorry, not shift plus 2. Select, click here and control plus 2. So control plus 2 will give you the 3D view of the structure. So you can just rotate it with the help of your keyboard direction buttons. WASD, which you use in computer games, this won't work. If you know what I'm talking about, but the normal direction keys will work. You can rotate the model, even just flip the model like this, you can do this. So get back to normal here, you can press Ctrl plus 0 to get back to normal, and Ctrl plus 4 gives you this 3D view which you can click and rotate around, which also, this is a rendered view actually. Just click here and Ctrl plus 4, this will give you the rendered view here like this. So these are the play around with the views just to observe the model, whether I have modeled correctly or not. So sometimes it's helpful. Okay, so now the properties are done. Yeah, and it's also helpful to give the presentation. Like if you want to do presentation or PPR something, you can use this 3D view. Just take a snipe of this and you can use it. Now materials, by default everything is concrete. Just select this and see, just check everything is concrete or not. If it's concrete, then it's fine. Just move on to the next. Now here in the specifications we have to do some things. Okay, so firstly we will define our go to beams here. Okay, then we'll go to start and release the moment at start. Okay, we again click on beams and then click on end here and release the moment mz at end. Only release mz. You can release the others also, but it won't make a difference here instead. Why, I'll explain in other videos, but you can also search it, you'll find the answer. So I've done one start and end. Okay, so let me just show you the example. I'll just go to front view and right click and click on the new view go to the portion where we'll utilize this. Okay, so this is the thing, and if you click on this also, okay, just click and hold also on a beam, you can see the green signal, green part and the right part. So green part is the start for every beam, and right part is the end. So in this particular option, both the green and the red, sorry, not the red, it's the blue, both the green and the blue, that is the start and the end, are pinned, that we have to release the moment. So they don't have any column to column connection here, so that's why you have to release the moment here. Okay, by the way, if you have any doubt, you can just pin the moment of the video which you have doubt, and you can just ask in the comments. I'll try to reply. Almost I reply all the things which I know. Okay, so just you can ask anything. So this has to be pinned from both the start and the end. So we'll just assign one for start. You can see this icon appears, which you can see, this denotes that is the pin connection, and again at the end we'll pin this. Okay, so like this we can use this pinned option. And then we have another option here which we can use here, that is the diaphragm. So earlier you can see that here we had the concept of master slave, but in the recent version, that if you are not using the select series, you can also have the flow diaphragm option, which the software automatically calculates. But the thing with the flows diaphragm is that if you apply the diaphragm before defining a reference mass, it gives error. So we can change this in the stat editor later. Okay, just assign it now. Later when you define the loading part to define the reference load for the seismic mass source, then you can change it later. If you're not understanding what I'm saying, that is for new, don't worry, everything you will know step by step. And if you request a video about seismic mass or whatever, I'll just tell you, or give the link to the video, or make a new video, whatever, just feel free to ask. Okay, so flow diaphragm we have to now define. So I'll select this define flow range first, and it's important that we know where to define the flow diaphragm. So diaphragm is an object which transfers the basically the loads from the horizontal or nearly horizontal elements to the vertical elements. So you can say basically beam to columns, slab to columns, basically like this slab or staircase to columns. So these are the diaphragms or these slabs. In simple terms, if we can put it out there, not accurate, but slabs. So I don't want to put if you put any slab here on the plinth level, you can skip it, or else you can put it also, that is not a mistake. Okay, so in this case, what I'll do, I'll put a diaphragm level at my plinth level, as well as a diaphragm level at the first floor level. You can do that, or else we can only do at the first floor also. Okay, let's do in the first floor level. So floor range in the first floor is 3 meters. So let me show you my diaphragm, utilities, node tools, node to node distance. So this is 3.2 meters, sorry. And in my this in our particular case, our plinth coordinate which are taken as 0, so the height will be 3.2, so it measures from 0. So if you have taken the bottom coordinate, some people like to make this foundation coordinate 0, so you have to add this height. Okay, so that's why I take the plane coordinate as 0, so that's helpful. Okay, so we'll go to node tools and remove the node to node distance here. So I want to apply diaphragm here, and obviously you can apply diaphragm here also, in the plinth level also. Okay, let's apply diaphragm everywhere, in this one, basically, but technically if we don't have a slab here, this won't act as a diaphragm. So okay, let's skip the plinth level, but let's apply here and one here. Okay, so it will calculate the center of mass and apply the reference load there. Or this is also useful for the application of wind load also. Okay, enough said. Let's go to the specifications and go to nodes and use the diaphragm option. So I'm creating 2 diaphragms, one for the normal this floor, for the first floor, and then one for the mounting. One height is 3.2, define floor range, select nodes. We'll select the nodes later, then for program and calculate, add. And another one, floor diaphragm. This is for the mounting or the headroom. Height is 3.2 plus 2.4, so 3.2 plus 2.4, it's equal to 5.6. So height is a 5.6 meter. Define floor range, select nodes, and then click on calculate. By default it will be calculate, obviously, and click on add. Don't forget to just click on this define floor range, or else you cannot select this. So I'll go to the front view, shift +1, and then go to select and go to select and go to use the node cursor, and for the first 3.2 height I'll select this. These the nodes will be selected. Here you can just recheck from this 3D view. These nodes are selected in red, and yes. Okay, and then you can go and select this and shift +1 again and select this like this, and use the cursor to assign. So these 2 diaphragms are assigned, but if you run the program now, it will give an error because you have not defined the reference mass. For diaphragm we need a reference mass, so define it later, because I want to go by sequence, not to confuse you guys. This is the process I personally follow, and I feel this leads to less number of errors, because in TAAD if you do mistake, it gives errors and warnings. So we'll create a fixed support here and select this and go to view and just see these supports here, assign, and yes. So the supports are fixed, denote the connection between the column and the footing. And I'll also make a video later, I think, to work around with other kinds of supports. So later, go to loading. Now support part is complete. Now go to loading. So now in the definitions, firstly we'll create the reference mass source. So if you are creating a seismic definition and you are using a reference mass in that, the definition inside the seismic mass will be preferred over this reference mass. But if you create the reference load, then no need to create any seismic mass source in the seismic definition. Hope you got what I mean. Means that in the reference load you can only create the mass source. Full dead load plus the percentage of the live load. That is, if the live load is more than 3, then you take the 0.50%, or else you take the 25%. So simple as that. Reference load here, this will be mass, and I'll call it mass only. So this mass will be used for both the seismic loads also, and I want to also apply the wind definition from here also. So wind 1, add, and I also already given the Excel sheet links here in a particular video. I'll give the link to that video, otherwise I need to create a new. I'll give the link to the Excel sheet. I'll search and give the link of the Excel sheet to you. So this wind type, click on add, And in this particular version which I'm using, the Indian code is not there, but in updated version Indian code is also there, so I'll have to use the Excel file. Those who have the latest version, they don't need to use that. Okay, Excel file. And by the way, if you want the Excel file, hopefully you find in the description of the video. If you don't find, by the means I forget, you just ask, or you just update this. Okay, so I'll just use this Excel file for the calculation here. And I'll not go into a lot much details because the page number and all you mentioned here, you can check. I don't know, video make this video long enough. The building is in Tripura, Agartala, so the basic wind speed here is 55. Terrain category is 1. This is the most possible terrain which you can have taken this, and everything you can just check from these pages here. By the way, these are the pages of PDF. Okay, page in code, sorry, pages in code, not the PDF. And search and find that. So we'll take the this at 2 heights, so at 3 and at 10. So just open the code for this particular K2 here. Okay, it's 75 part 3 2015. This is the wind code. And yeah, for terrain category 1 at buildings less than or equal to 10 meter height, the K2 is 1.05. so basically which means that only 1 is enough here. So for 10 and 3 they will be same, it will be 1.05 here. Let's keep 1 only, 1.05, and the pressure will automatically calculate 1.459, which is the pressure here. So we'll go to STAAD and put the height 3 and 10. So, and for both these pressures the PD will be 1.459. okay, so 1.459 is the PD here. Yeah, so this is a PD. Click on add and click on close now. So go to seismic definitions. We'll define the seismic definitions here. Select the IS code for the IS 1893/2016, latest code and the date currently which you have. Click on generate. This is the zone 5, and RC buildings with special moment resisting claim should be selected. Now importance factor is 1. I've just also got a detailed document for this also. You can check this out, the earlier videos also. Soil will take as medium soil, and this comes in all other buildings here. Why the all other buildings? Why not RC moment resisting frame? I've made tons of videos on this, but if you want, I'll make another separate video also. Just let me know. If you don't know this, I'll just tell you. So this is it. And time period you can calculate, and you can put it out there. You can let the software calculate itself. If you let the software calculate, then it will give you a warning that it is calculated at the plinth level. So you can calculate this also directly. So I think we'll just have to open that particular document which I'm talking about, to make sure that we have this response spectrum analysis stat. I'll also give you the link to that if you don't have this already, which I've made for all of you guys to use. Okay, so first of all, for the time period, we'll just have to go here, and this is the time period here, which is this time period for all other buildings here, is this formula, and the building dimensions you need to know. So here the let's take the building dimensions here, we need to know, right? So okay, let's just click on this generate now. We'll click change this later. Okay, generate and click on add, and then close. Change this later now. So this is the x direction, this is the x direction, and this is the z direction. So let's go to utilities, node tools, node to node distance, x, z, building height. In building height the headroom is not included, so 3.2 the building height. So here let me go back to this file which you can also open. building height is 3.2 meter, and in some cases building height can also be the height from the ground levels, but we'll take this 3.2 meter. And the building dimensions here, center to center at 9, in x it is 6.576, 6.576, right? 6.576. And in z direction it is 9.026, so it is 9.026 here. And 0.09 into the building height is 3.2 meter, 3.2 meter into the height of the, sorry, into the dimension of the x and z, so 6.576. so you can see the steps are long, because if you do it accurately then the steps are long. I cannot make a clickbait video like in design in 30 minutes, 20 minutes. I cannot do that if I go by the exact same process again for a small building. Imagine how much time it takes for the large building. So yeah, it is what it is. Okay, so I'll use Excel to calculate this. Maybe 0.09 into 3.2 equal to 0.09 into 3.2 and divided by square root of 6.576 equals to SQRT 6.576. And I'll just copy the command here, and I'll just copy this value from here. 9.026 is the value, right? And I'll paste it here. So it's 2.56 and 3. Is this accurate? 0.03.2 and divided by square root of 6.576. okay, it's small building, so that's why I'm not used to these values. 2.56 and 3. No, this is not supposed to be that much. Oh, sorry, I have to divide this. Sorry. I'm just so confused in this. Okay, so this is the accurate value, 0.11 and 0.09. so let's take this 0.11 and 0.09. so let's take this as 0.1 and let's take this as 0.11. okay, so 0.11 and 0.1, so 0.11 and 0.1 in this both directions. Now just go to the STAAD file and go to the definitions, and then we will go here, and the seismic definitions will just change this, edit this, and here period in x direction and period in z direction. X direction 0.1 and this also 0.1. okay, so this is the thing. We can change this and change, close, change this. Now go to utilities, go to node tools, and remove the node to node distance. So the node to node distance is removed. So this part we are done for now. Then you can go to the load cases and create the load cases here, and the first load case will be seismic SLX. I'll just explain later the SLY y direction, because it is in seismic zone 5 and you have to add in y direction seismic zone 5 also. If you're not in seismic zone 5, you don't need to do this. I'll just show you the clause also, what process these are required here. So SLZ, and then we add the dead load DL, then we add the live load LL, and then we add the wing loads W1 for the 4 directions. So W2, this W3 and W4. Okay, good. Close. Seismic load in X direction. Seismic load in X direction. So go to seismic load, X direction factor 1, add seismic load in Y direction. Seismic loads here, Y direction factor 1, add, close. Seismic load in Z direction, seismic loads, okay. Dead load, first of all we add the self weight, then we add the member load. Member load, there's the wall load. So the wall, if the wall is 3.2 meters height, deducting minus 0.3 for the beams, so 2.9 into 20 is the unit weight of brick plus plaster combined, approximately, into for the 10-inch walls. If we're giving like this, you can take 0.225, or in this case we want to take actually 0.125 5-inch walls everywhere, so 7.25. So 7.25 load will apply here, minus 7.25, minus because it's actually from top to bottom here along the gravity direction, that's why. And they add this, and then we need to add the slab load. So before adding the slab load, I'll just want to tell you something. Going to the front view, selecting this and going right new view and click on OK. So here for the proper load distribution, we can divide this into the one-way and two-way slab distributions here. So definitely this portion will have the staircase, so it will not be there will not be any slabs, but you can check the note tools for the load distance. This for this particular slab, for example, because other slabs are two-way slab, from checking only we can see. So for this particular slab, let us check here. So it is 3.288 divided by 2.075, enter 1.58. So it is less than 2. So if it was more than 2, then it would be one way. So now it is a two-way slab. All these slabs are two-way slab. Others we can see by the dimensions itself. So we'll go to node tools and remove node to node distance here, and you can group the slabs, actually portions where you will have the slabs here like this, and then assign this as two-way slabs. Otherwise you can assign directly, okay, because if there is one-way slab, then we need to do that one-way, two-way, using groups also. Maybe I'll show you this in another video. Just add the flow load here, because anyway it will act as two-way slab, okay. So here the pressure calculation. So let's assume a slab of 125 mm, and the unit weight of concrete is 25 kg/meter cube. We know that 3.125, and plus some floor finish of 0.5, okay, tiles, whatever you are using. And since this is the top, we'll also add on the top of some waterproofing of, let's say, let's go 0.5. So it comes as 4.125. let's go on the higher side and take 4.5 as the flow load here, minus 4.5. And the Y range, we'll define the Y range here. Minimum Y range, let's go 3.1 and maximum. So maximum will be 3.2 and minimum 3.1. So it will exactly be in this floor according to the height of the building. Click on add and click on close. So you go to view, we go to this level structure, and then we will see this will be assigned automatically. You can see the blue selection is the part which is this self weight, assigned to view, assign and yes. And this particular weight, I can add another load for the parapet wall as well. Member load for the parapet wall, we calculate, let's take 1 meter height, 20 unit weight of brick, and let's take 0.25, like full 10-inch walls for the parapet for safety, 5. So you have this minus 5 for the parapet, which will add close. So first of all, 7.25 is in the this floor. So right click and click on new view, and click on OK. So we go to the top view. Now you can apply in the places where you have the walls. Let me apply on everywhere. Okay, you can see the plan here. The PDF is still open. Okay, PDF I've closed or what? Oh, I think I've closed, but yeah, no, I'm not closed. So you can see everywhere we have walls here. So pretty much it will apply. We applied everywhere here. So this will be applied everywhere. Assign and yes. Okay. And this 5 kilonewton is for the parapet walls. So let's go display whole structure. Let's go to the front view and select this and right click and new view. Click on OK. Go to the top view and in this particular view, click on this 5. So apart from the staircase here, first of all I'll just select a perimeter like this. About the staircase portion, everywhere we'll have this particular load, and in the staircase we'll have this load. Okay, so this is defined, this is defined. Did I define this in the whole entire structure by mistake? Maybe I think I just did this assign to view. In that case I'll just delete this and we'll add a new load here. Not new load, sorry, add load, member load and -5. I think I did assign to view that also. So the selection assign to selected views, assign yes. So this is done, and now it's time for the live load here. So live load, I think I'll use the editor file, utilities, go to the editor file to copy the live load first. So this member load is this one. So live load for the residential building is 2. So we'll just take -2 here and save this, and then we'll close this. So we'll go to the loading part and we'll see that this live load has been assigned. Oh, this is wrong. This one is it's -2. Go to loading. Now it's correct. Okay, so seismic load, dead load, live load defined. Now so once you have done this, you can define the seismic mass source. Dead load and live load has been defined. So let's define the mass source here, and then we'll go to the wind load here, go to the command file. By the way, in the updated version there is the automatic option to define the mass, but not using that version, or the older version, so that's why I have to define it like this. So first of all, we'll just copy this self weight part, dead load part, and let's find the reference. This one is the reference load type mass. Okay, and in this between we will insert this. Only there will be no negative sign, and it will be applied in all the 3 directions. In case you are applying only earthquake load in 2 directions, then we will go 2 directions. So, okay, so it will be X, Y, and Z. Okay, and then the member load also, there will be no direction, and it will be applied in X, Y, and Z. So you can remember the code: full dead load plus a percentage of the live load. Okay, percentage will be 50% for more than 3 and 25% for other things less than 3, less than or equal to 3. Flow load, no minus. gx, gy and gz, right? Let's also copy the live load part. Live load is 2, so you remember that. Just copy this, copy one of them. Live load is 2, right? So okay, you can basically just for reference, because you may use this video for other video tutorial, just copy the live load here like this, because in this case the range is same, but actually the range might be different, and delete this flow load option, and here go for the percentage. So it is 0.5 for 25%. Okay, and now it is for x, and then for y, and then for z. So for y, you get it, y, to turn the caps lock on, right? Z, right? So this is it. This is the reference load definition, but this reference load definition here, it must be before the diaphragm definition. So control plus x and just put this, I think after the member release I'll put it here. Okay, so that I don't have any errors. Okay, and by the way, if you want to see the earthquake load applied in y, there is in 3 directions as well. I think I have the clause here. If not, I have to put it. Yeah. Yes, this is the clause. No, it's not a clause. Okay, this is the clause 6.3 in the seismic code. That is 2016. Page number 8 of the clause. So affected to vertical earthquake shaking shall be considered any of the following conditions: structure located zone 4, zone 5, planning inequalities, rest on soft soil, bridges, long spans, like this. So if your structure has any of these criteria, then this would be followed. So that's why. So that's why this is it is what it is, and we have done this to this. Then go to loading, and here live load is defined, seismic mass source is defined, and we can analyze the structure by the way. But first of all, we'll go to specifications, and we'll go to beam here, and here property reduction factors here will apply. If you take out my not it's our, because you are also using is, take out my notes or our notes, then you'll find this clause 6.4.3 per, and moment of inertia shall be taken as 70% for columns and 35% for beams in RCC structures. So exactly we'll do this. So moment of inertia, there are two moment of inertia here, both will do 0.35 and 0.35 for the beams, and for both of them property reduction factors will do 0.7 and 0.7 for our columns. So this we are applying here, and we'll apply on the beams here, parallel to x and parallel to z. This is for the beams, assign and yes, and this is for the columns, parallel to y and assign and yes. So yeah, this is it. These are the assignments here, and go to analysis and design, and analysis command. First of all, click on all and click on add. This might give some errors now, but let's anyway see the empty load cases, because the wind load doesn't have any load cases here. We have two warnings here, two errors here. So let's see, and just fix those errors first. Okay, so I think we have, so the error in support input, there is no support, analysis will not continue. I think we need to define a reference load before the supports, or something like that. This let's fix that. So because we have defined the supports, right? So supports need to be defined before this. Okay, what if I move this supports to after members cracked, or members concrete? Now just change the order and then analyze, because there's a little bit long structure. I don't want the let's see the warnings here. So the two warnings will be, so this base dimension and UVC analysis. So let's remove these warnings also. Base dimension calculated lowest support. Let's fix this part. So for fixing this part, what you need to do, you need to go to command file, and here let's look at the seismic definition, seismic load definition here, ST5. Just remove this ST5 here, SS2 ST5, remove this, delete, space, Ctrl plus S, and let's just watch what is the analysis result. Now there should be two warnings, one warning now if this works, otherwise yeah, one warning. So now another next this warning I'll just show you, and then we will remove their warning here, because we want no warning. This UVC has tension compression. Let's remove this warning. So for removing this warning, go to command file, and here we'll just in the seismic load definitions we'll do add one command, perform analysis, and then we'll add change, perform analysis change. Now just copy this and paste it in all the seismic load definitions. Ctrl plus S and close, and this is done. And then run the analysis once again to check. So for now you have 0 warnings. That's fine, that's fine. Okay, so here go to loading here, and then let's continue defining the wind load here. So wind load definition, my wind load definition is not perfect, but this method which we are using here, that saves little bit time, and in the outdated version you can apply perfectly, and this version also if you're using you can apply perfectly, but it will take a little bit time. Maybe I'll make a detailed video on that some time, but this process should be design the building on a safer side, so there should not be any problem. But if in a wetting the accurate process is required, then we have to go by the long method. But for most buildings you can use this method, though it is not accurate as per our codes. Okay, so that's why I'm just giving this disclaimer. So X direction, I want to apply the wind like this here. By the way, the code says like the X direction you have to apply like this, windward and then leeward, but I'm just applying wind everywhere in the windward phase in all direction with a factor of 1. And basically in the accurate method, some place there will be 1, there will be 0.8, there will be 0.7, like this it comes. But let's go by this method for the approximate wind load calculation here. So X direction, windward phase 1, and we'll select the node cursor and see the nodes here. This X is 0, and here in this phase X is 0, and so X, Y range, maximum range, let's give this 1, so that will maintain this range. And Z is 9.026, and this one it is 0, so, and Z is 0 to 9.5, let's give. Okay, and Y, obviously you know this start from the plinth level to here, headroom or empty room is not included, so it will be 0 to 3.2. okay, windward phase, click on add, yes, and then we'll close this. So you can see the wind is applied like this. Okay, so in the accurate process only it will be applied here, and then here in this direction, and then from the opposite direction like this. So it will have to create 4 load cases. I'll make a separate video on that, but this is the approximate process. So just telling you. So this one also I'll apply in the X direction, but in the opposite phase here. So windward, so wind load, windward, X and Y range, let's define maximum is 3.2, and X range, let's check here, node tools, X range, rotate the structure a little bit to get this node, like this. I'll rotate. Okay, now it's fine. So the minimum X range is this is 6.576, and this is also 6.576. So let's give the X range to 6.5 to 6.8, right? And in the Z range, here it is 9.026 and here it should be 0. So let's give 0 to 9.5, and let's check the, let's click on add and we'll close this and check the direction. Here it is applied like this, so we'll apply it minus, we do -1, then we'll apply it from this direction. So we have two wind loads applied in the X direction, this one and this one in the opposite face, all acting along the windward face. Okay, so click on add here, and in this particular thing, go to wind load, and here minimum Y range is maximum Y range 1.2, sorry not 1.2, 3.2, and then this will be Z here, windward face, and then this range X0 and X 6.576. so X will be from 0 to 6.8, let's give, and Z is here 9.026 and here it is 9.026. so let's give 9 to 9.1, minimum 9, maximum 9.1, and add this, close this. Now see, this is acting the opposite direction, so just give this -1, lag from there. Okay, now the last but not the least, obviously, W4. And now here in the W4, so we'll go to wind load, and in the wind load obviously Z direction, minimum maximum will be 3.2, X range, let's go, this one 0, this one is 6.576, so let's go 0 to 6.8, let's go Z range 0 to 0, so let's go from 0 to 1, click on add. So it's applied perfectly this time. So let's also analyze the wind load here with wind load to see if there is any error in the diaphragm, error or warnings in the diaphragm here. So 0 warnings, 0 errors, so we're fine, no need to change anything. Now you can say kind of that the static analysis is complete, except we have not defined the load combinations, but we have to go for the dynamic analysis of this one. So there is a lot of debate regarding this, whether it should go for the dynamic analysis or not, but the IS code is clear. If any structure is in zone 3, zone 4 or zone 5, we have to go for the dynamic analysis. Let me just show you. I'm not saying this, the code is saying this. So for the proper structural design, you have to go for the dynamic analysis. Here, if you just observe this particular document which I've given here, you can easily find out this thing, but anyway, I'm just showing you. Okay, so these are the processes which I mentioned. So ensure modeling is complete. Modeling is complete here. Earthquake is provided in 3 directions here. We have explained this, and time period is also calculated here. And let me just copy this time period here. History time period. Seismic mass source is provided. Seismic weight of the float is the dead load plus weight amount of live load here. And then this is the percentage. Table number 10. Float diaphragm is considered flexible or rigid. Here consider flexible, and this is also provided. Now response spectrum functions, we'll add this response spectrum functions here. So now for this response spectrum loading here, let me just paste the time periods here. Now for both this, you can see as per this response spectrum, as per this 6.4 clause, and this SA by G is 2.5. so if SA by G is 2.5, Z for the zone factor zone 5 is 0.36, 0.36 by 2, 0.18, so 0.18 into 2.5, and response reaction factor is 5. This one you can see 0.36 is for the seismic zone 5 in test table 3. Response reaction factor defined table number 9, importance factor in table number 8. Everything is given here. So you have to calculate this. So in the x and the z direction, it is coming as it is coming as 0.09, and the vertical direction, for the vertical direction you can refer page number 14 here, this formula. So it's coming as 0.06. So this is the response spectrum definitions which you need to take, and you can also consider eccentricity here, which the STAAD.Pro automatically calculates. Okay, and you need to apply the load combinations. For the 2 direction it is this one, and for the 3 direction these are the load combinations. So you have to take the load combinations from a file which I'll provide, which I've made for you, and then you can literally just copy and paste the load combination, because STAAD.Pro will not consider this load combinations if you go for the automatic load combinations here. So that's how you need to complete the remaining thing. Okay, so go to the loading part, and here we'll add the 3 more loads here. Primary, so it will be response spectrum, seismic, RSX, RSY, RSZ. Okay, and then the response spectrum is, we'll go start as CQC. You can just select the code here. Our code is 2016, medium soil, and then we apply next direction, and next direction it is 0.06 times the base shear, and you will use the torsion part as well. Okay, so you can use this torsion part, or you can skip this torsion part. Let's skip this torsion part for now, for this one. But if you want to use this, the dynamic eccentricity and accidental eccentricity, so it is basically you can use this values here. Where to go? This one. So dynamic eccentricity, and the next one is the accidental eccentricity. So you can use, so basically if you use the torsion, then you have to calculate this according to this 2 formulas here. So you have to calculate plus and minus, you have to take. Okay, so let us just skip this for now. Eccentricity and scale we can define later. Automatically STAAD.Pro will give the scale if that is required. That is, the dynamic base shear is less than the static base shear, give the scale. We can insert this here later. So this is the process. I guess you will use the CQC, medium soil. Damping is 5%. Click on add, and then we'll click on close. So then in the y direction, same thing. Select the code, select the method, select the soil type. This is in the y direction. I think I've just done something wrong. I feel that in the y direction it is 0.06, and the x and the z is 0.09. Okay, I'll change that later. 0.06. Okay, I think you can use the STAAD editor to change that. Sorry for the mistake. 0.09. Let's apply the Z in editor itself. Okay, damping response spectrum definition has been done. Okay, now let's run the analysis here. Zero warning, 6 nodes. Let's see the 6 nodes here. Okay, let me explain the system. Mass model we found for the time history response spectrum. So this is not any problem here. Mass model will definitely be found from the reference load case. Equivalent static method shall be performed for regular structures for natural time period less than 0.4 seconds. and with structures less than 15-meter height in seismic zone 2, reference clause 6.4.3 and 7.6. So this clause was added in this new code. So refer to this clause. That is why we should refer the dynamic analysis. So because we did both dynamic and static here, so that's why this message has been shown. So obviously you should do both dynamic and static in the particular file, because that way you'll know what to put for the scale factor. Okay, so our scale factor for our acceleration or the in the response spectrum case is more, or the base shear is more than that acceleration for the static load. So that's why you don't need to apply any scale factor or multiplying factor for the VB. Though the dynamic base shear is more than the static base shear. If it is less, then we have to apply the scale factor, and STAAD would give a message in this. There's no message is given. And about this floor wave one-way load, because if we just group and apply the loads, then it is a more accurate way of applying the load. That's what they've told. So I've also done a video on group, you can check that out. Just you have to apply the groups and you can apply the particular flow load to that particular group. But since we don't have any one-way slabs in it, this should be accurate. There are no any other concerning messages here. Okay, so this is the final matrix, because as you know, STAAD follows the matrix method here. So this matrix which is available here. So this not should be any concerns in this messages. Okay, so final step, not final step, almost the final step, we'll go for the load combinations. So we'll go to utilities, we'll go to command file, and since everything is remaining thing is accurate, we'll apply the load combinations here. So for that you have to go to my file, which you can download if you have not already downloaded. No need to download again, because it's the same file. Okay, which we have provided. So otherwise you can download from the link here. That was it, project 9. So this load combination sequence is for this particular load also. Only if you just change the sequence, then like which load comes or which load, then you have to make your own using the code, or you have to edit the things a little bit. Okay, so that's what I'm saying. These are the load combinations prepared already. For the wind load also it is there, and just Control plus C, Control plus V, and perform analysis will happen. Close, and hopefully there shouldn't be any error, I suppose. Error warning chance is less, because we have already cleared out all the warnings earlier, so that's why. Now we can go for the design here. Go to utilities, and in the utilities you go for, not the utilities, go to design, and in the design go to analyze the design. Concrete, select concrete IS456. This is our code. Select parameters. We'll select the parameters which are absolutely necessary. I'll use the minimum main. Okay, maybe 500. Commands, design beam, design column, design column. Okay. Okay, so you can see the design from here, 420. So since the dynamic analysis, the results will be a little bit on the higher side, as you can see, but still it is like safe and all, no problem. You can see beams are passing easily. There's not many problem, okay, available. So you can see this is the design here, and if you want to go further, you can also design this in RCDC using the process which I've shown. So I'll not design this in RCDC because to just to make the video a little bit longer, but you can watch out the other videos and design the file in RCDC and make the final output drawings. That's all for the day. Hope you like this video. If you have reached the video till now, make sure to drop a like and also comment for if you have any kind of doubts. Thank you. Bye bye.